Tammy, thanks for the invitation. Very nice time in the Institute so far. So obviously, we heard the joint work of Joni Teravainen on what we can say about some old conjectures in number theory if you assume it's equal to 0. In particular, the Chowla and the Hardy-Littlewood conjectures. So let me just remind you what they are. Okay, so the Chowla conjecture can be stated for either the Lubel or the Mobius function. I'm going to state it here for the Lubel function. Lubel function is the multiplicative function that equals -1 of the prime. So lambda of n is 1 if you the product of an even number of primes, is -1 if you have product of odd number of primes, counting and the Chowla conjecture is that all the correlations of the Lubel function are asymptotically 0. Okay, so asymptotically, the Lubel function should look like a random sequence plus minus ones. And the precise statement is that you take any distinct integer shifts h1 to hl, and you look at this correlation. You take lambda of n plus h1, multiply all of the after lambda hl, and you average. Okay, so this notation is the notation I like to use for if you average between all the numbers from 1 to x. This average is bounded by 1 by the triangle inequality, but it should actually go to 0 as n goes infinity. Okay, so for the ergodic theorists in the audience, means that the limit system of the Chowla of the Lubel function is the Bernoulli system. All right, so this is the Chowla conjecture. It's more or less completely open, with caveats. Okay, but right, when L is 1, it follows in fact is equivalent to the prime number theorem. The higher cases are technically open, so there's no value of h1 to hl for L bigger than 1, for which this particular statement is proven. Although if you allow some averaging, so either if you average the h1s and hls in some large enough set, or if you also average you replace this simple average by a log average, there are some partial results which we will not talk about here. And also, there's also been some recent progress in the function field analog of this for certain function fields. As I said, I'm stating for the Lubel function. You can also state it for the Mobius function, which is the same function as Lubel, except that you restrict to square free numbers, and they're not known to be exactly equivalent, but they're sort of morally equivalent in that whatever progress you can do on one, you can pretty quickly get for the other. And it's connected to a couple other conjectures. I'll just mention that it implies a well-known conjecture of Peter. That the Lubel function should actually be disjoint to all 0 entropy sequences, asymptotically orthogonal. And actually, if you do enough averaging, they're actually equivalent. All right. Okay, so this is the Chowla conjecture. Now there's an analog for, so that was for the Lubel function, which is denoted little lambda. And there's another function in number theory called the Vomangot function, big lambda. So I didn't define it, but big lambda of n is the function which is lambda of n is equal to log p, n is a power of a prime, and 0 otherwise. So it detects prime. For example, lambda of 2 is log 2, lambda of 3 is log 3, lambda of 4 is log 2 again, lambda of 5 is log 5, lambda of 6 is 0. So it's a kind of irregular function, but it's on average is equal to 1. That's the prime number theorem. And there's a similar conjecture, it's called the Hardy-Littlewood conjecture, or the Hardy-Littlewood prime tuples conjecture, which actually I also talked about in the previous talk. But anyway, so is that if you take distinct integers h1 to hk and you look at the correlation, k-fold correlation of the Vomangot function, this time it doesn't go to 0. You don't expect that because lambda is positive now, non-negative. But it should converge to a very explicit quantity called the singular series, asymptotically as x goes infinity, and this is just some number that depends on h1 and hk. One way to define it is that there are local analogs of the Lubel function mod p. So if you project the Lubel function to the Vomangot function to residue classes mod p, the prime number theorem in arithmetic regressions tells you that asymptotically the projection looks like the indicator of all the residue classes that are primitive, co-prime to p, normalized by this extra factor p over p minus 1. And so for every mod p, every prime p, there is a local analog of correlation, which is just some rational or some explicit rational number for each p. And it turns out that these numbers converge to 1 fairly quickly. And if you multiply them in p, you will get some fixed constant, which can either be non-zero or 0, but it will be some fixed constant. And you get around like this. For example, if you take lambda of n, lambda of n plus 2, which comes twin primes, I think this constant is like 1.3 something. I forget exactly, but these are all they're fairly well understood what the single series is. But the right-hand side is not difficult. It's the left-hand side which is hard to understand. Okay, so this is the Hardy-Littlewood conjecture, and very similarly to the Chowla conjecture, we know it for k equals 1, based upon number theory. And there was no value of h1 to hk for which we know it for any bigger value of k. It's completely open. And here we know less than in Chowla. Again, if you average in the h's enough, you do eventually get some results. But other than that, again, there's a very nice result of Sauer and Schusterman, which gives you a function field version of this, but only for the 2-point correlations, and only for certain function fields. I think the field has to be FQ, where Q has to be at least like a cube or power prime, I think exactly. And it's hard. I mean, so even k equals 2, the first non-trivial case, that implies a trim-prime conjecture, which is of course one of the most famous open problems in number theory. Okay, so these are tough conjectures. But one phenomenon we know for some time is that there's one case where we can actually do something. Oh, hang on, before we do that. So of course, you can always make life harder. You can combine the Chowla conjecture and the Hardy-Littlewood conjecture into what I call the Hardy-Littlewood Chowla conjecture. So now you have, say, k shifts for the von Mangold function, and O shifts for the Littlewood function, and if they're all distinct, the conjecture is that if you multiply them all together and you look at the mixed correlations between von Mangold and Littlewood, that there'll be an asymptotic. And the asymptotic will either be 0, so if there's at least one lambda in this product, so if L is positive, then the random fluctuations of the Littlewood function are expected to completely cancel this cancellation. And asymptotic, you get 0 if there's at least one factor of the Littlewood function, but if there's no factor of the Littlewood function, you get the singular series that I described in the previous slide. If you like, what's going on is that mod p, the reduction of lambda mod p is this non-trivial function, but the reduction of little lambda mod p is 0. So there's an explicit conjecture as to what this is. So this is just sort of the natural unification. I mean, it's stronger. It implies both Hardy-Littlewood and Chowla, and it also controls some mixed correlations that were not controlled by either conjecture. And of course, since this is harder, it's even more open. So I mean, the only things that are known basically are the cases where k plus L is 1 or 0. Okay, but it's just to state those results, it's easier to work in this unified setting. Okay, so so these conjectures are hard, yeah, well, Chowla, there's maybe a chance for breakthrough in the next few years. Hardy-Littlewood, I don't think we are close, but especially if you just averaging Chowla, but there's one case where we do, there's sort of one scenario in which we can make progress. And that's if you assume something go to Siegel 0, also known as an exceptional 0. So you can get very strong results. The catch is that these guys probably don't exist. But still, it's a good alternate universe to investigate. So just to recall the definitions, okay, so Siegel 0 is a real number beta, it was between 0 and 1, and it's a 0 of an L function. So it's associated to a certain Dirichlet character, and actually a specific primitive Dirichlet character of some conductor, Q lambda, which I think has to be a primitive discriminant, if I'm not mistaken. But anyway, there's some quadratic character which gives you an L function. And L functions, the zeros are supposed to be on the critical line, real part of S equals 1/2. That's the generalized Riemann hypothesis. But perhaps, as far as we know, that may fail, and there may be 1, 0, which is really, really close to 1. So I guess this is the S plane. The L function has no zeros to the right of 1, and it might possibly have a 0 very, very close to 1. And if the distance is a lot less than 1/log of the conductor, we say that it's a Siegel 0. Okay, so the precise definition I'm giving here is that if beta is equal to 1 minus 1 over eta log Q, where eta is something big, and it doesn't really matter what big is, because they're bigger than 10. This eta I'm going to call the quality of Siegel 0. So the bigger the eta, the closer the 0 is to 1, and somehow the stronger the Siegel 0 is, and you get more and more stronger results as the 0 gets closer to 1. Okay, so this has been, Siegel zeros have been a thorn in the side of analytic number theory for at least 50 years, because they kind of provide counterexamples to all kinds of things. And if they exist, they distort all kinds of asymptotics in number theory, and we'd like to get rid of them. And there are many attempts to do so. As I said, if you assume GRH, it's assumed that they don't exist. That implies that they don't exist. We do have some control on Siegel zeros. So most famously, we have Siegel's theorem that says that while Siegel zeros exist, they can't be too horrible, and that they can't be super strong. The quality, which measures how close you are to one, has to go slower than the conductor. Okay, so for every epsilon, eta is less than some constant epsilon times conductive epsilon. So that's already quite a useful bound. We would like a much better bound. Despite many attempts, we don't yet have one. There's this famous catch for Siegel's theorem, is that this bound is famously ineffective. We have no formula for the constant epsilon. Although I will say that somehow the problem is confined to exactly one Siegel zero. Okay, so there's an observation in Tao that there is an effective epsilon for which this bound is true for all but one character. I just can't tell you what the character is. Of course, it doesn't exist. That's what everyone believes. But anyway, that ineffectivity is another thorn in the side of theory. Okay, so they can't be super strong. They're also pretty rare. I mean, we assume they don't exist. Okay, so I mean, we believe they don't exist, but if they do exist, they don't show up very often. So there's another theorem called Lando-Page theorem that says that they repel each other, and really high quality Siegel zeros repel each other a lot. So one version of this theorem is that if you have one Siegel zero beta with some quality eta and some conductor, then there's no other Siegel zeros with any larger conductor between the original conductor and the conductor to some constant over eta. So you can't really have two different Siegel zeros which are sort of within polynomial size of each other. And the stronger the zero, the larger the region in which it pushes away all the other zeros. So basically, in any kind of dyadic range, there's at most one Siegel zero that is possibly a problem. Yeah, we would like to say that there's zero zeros with okay, but there's at most one. Okay, so these are sort of the basic facts about Siegel zeros that you'll learn in any graduate number theory class. Okay, and so it's been known for quite a while that one way to actually, so in some ways it's the enemy because it messes up things, but Siegel zeros also actually make life easier in many ways. There are certain things you can do in the Siegel zero universe that you cannot do in the expected GRH universe. So for example, we can prove the twin prime conjecture if you have enough Siegel zeros, whereas we do not know how to prove the conjecture on GRH. And so this was an old observation of Heath Brown. The specific result is that if you have one Siegel zero beta with some conductor and some quality, and you want to control a pair correlation, okay, so think of, for example, lambda of n, lambda n plus 2, so that counts twin primes, then the number of primes up to x on average is what it is expected to be. So the Hardy-Littlewood conjecture predicts a certain singular series. In the case of twins, I think it was 1.32 something, plus an error which is not great, but it gets better as the Siegel zero gets stronger. But there is another catch. This is not a formula that holds for all x. The x somehow has to be in range of a Siegel zero. So somehow each Siegel zero controls, somewhat exerts, has like a little kingdom where it sort of exerts its influence on number theory. And roughly speaking, at scales slightly bigger than the conductor, the Siegel zero gives you a lot of information, and then it tapers off, and then you lose information. So what Heath Brown showed is that if x is a polynomial size in the conductor, and specifically he gave these exponents between the conductor to the 250 and conductor to 500, then you get this asymptotic, but he doesn't say, but if x gets bigger than that or less than that, he doesn't claim anything. Okay. So one corollary of this is that, so this by itself doesn't quite prove, so a single zero does not actually give the twin prime conjecture because it only produces twin primes in one range. But one corollary of this theorem is that if you have an infinite sequence of Siegel zeros going to infinity, so they repel each other, so they can't be too close, but in principle, there could be an infinite sequence. And if their conductors, or if their qualities went up to infinity, in fact, or not even up to infinity, just specifically larger than a large constant, then this theorem would imply twin primes, the twin prime conjecture. Okay, so it's sort of, in the universe of possible behaviors of L functions and so on. On the one side, there's the GRH, which is where we believe we live in. And then there's this opposite alternate universe of Siegel zeros. And then, of course, there's this huge messy unknown in the middle where there's neither Siegel zeros nor GRH. That's the worst possible place to live. So we don't know which of these places we live in. GRH is somehow where we want to live. But the other extreme is actually is somehow not bad in some ways, and that we can prove things. Sometimes not the things that we expected to be true, but we can prove things.
By the way, Terry, it's Peter. I'm participating from the sidelines. In this world you talk about, there's some people who like to believe that maybe the Riemann hypothesis is true except for these Siegel zeros. But that's not possible.
Yeah, I know.
If you assume that you just have them real, then it cannot happen. So it's kind of a
right. Yeah. So that was work with was it Jacobson or something? Yeah.
Zacharescu and Stark also observed it.
Yes. Yeah. No. That is very. Yeah. So that is a nice result of Peter and you can't just have zeros on the critical line and Siegel zeros. You have that, you must have also some additional zeros as well.
Okay, while I'm about it, then my only complaint so far, I'm sure I won't have any more, is that you didn't say Siegel zeros in your title. One Siegel zero is not going to help you prove twin prime, as you just remarked.
Yes. Okay. So So I will also note that in my talk I will talk about is the word type. Okay. So.
Okay. All right. You win.
Okay. We will focus on non-asymptotic results at one scale. Yes. Okay. All right. But this is motivation. Okay, so all right, now Heath Brown showed that under the Siegel zero hypothesis, you do get twin primes in at least one range. Okay, but as Peter said, if you want an infinite number of twin primes, you would need an infinite number of Siegel zeros. Okay, but we will usually just assume one Siegel zero. If you assume one Siegel zero with the same notation as before, there's a result of Germanica tie that is an analog of Heath Brown's result for the Chowla conjecture. That you look at, say, for example, this pair correlation of the Looper function, you also get some decay in the quality of Siegel zero, plus a term which goes to zero as x to infinity in some explicit way. But again, only for a certain range. Right? X has to be about polynomial size in the conductor, so they get a slightly wider range. So Heath Brown goes between q to the 500. This is between q to the 10, and q to something that begins to grow a little bit with the quality. So the higher the quality of Siegel zero, the larger the range for which you can actually say something. Okay. This result was extended more recently by Chinnis in 2021 to multiple correlations. If you take L-fold correlations, you have a similar statement. The bound got a bit better. Previously, it was like double log in the quality, and now it's actually single log in the quality. But the range is about the same. Okay, so what Joni and I were able to do shortly afterwards is have a similar statement with the generalized, the combined Hardy-Littlewood Chowla conjecture. So that if you want to look, if you have one Siegel zero and any just sort of fixed collection of shifts, and there's one important caveat. We can handle any number of Liouville function factors, but we can only handle at most two factors of the one-manifold function. And this seems to be a serious limitation on the state of the art. I'll explain why later. But for this multiple coupled interaction, we still get the expected asymptotic, so the expected singular series, which is zero if there's a Liouville, or the singular series if there's not a Liouville function, plus again a log type error, and we get a somewhat slightly bigger range. So q, x has to be bigger than some power q, but less than, we cannot get q to the 8 and 1/2. So there's a larger range for which we can prove the but again, as this is just for a single scale, if you want to use this to produce an infinite number of k tuples or something, you would need an infinite number of Siegel zeros. Okay. Subsequently, this result, one case of this result has been sharpened quite a bit. So then there's if you restrict back to pair correlations of the von Mengele function, so twin prime type problems, But they can also handle Goldbach type problems now. So no Liouville, just with 2 copies of Mango. They actually, more recently, Matamaki and Mirakowski were able to get much better bound, actually. So we were getting a log type bound, and they actually got more like quasi-polynomial type bound in Ada. There's a parenthesis I'm missing there. Well, okay. Well, that's if X is not too large. Okay, so let's say less than Q to the 10 log Eta. They can actually get results up to Q to the Eta to 1 minus epsilon. But then the bound becomes a bit more complicated. I didn't want to write it down here. When I think about their work, well, first of all, they managed to simplify. They had a simpler argument than ours. But also, our result, this big O depends very much on the choice of shifts. Okay, so basically our shifts have to be bounded in order for this argument to be useful. They actually get bounds that actually, I mean, I stated it for fixed H, but they actually get bounds that work for any H as large as X, pretty much. I mean, the constants do depend on H, and particularly on how many primes divide H, so forth, but in a very explicit way. They track the dependence on H. And because of that, not only do they get twin prime type results, they can also understand the asymptotics for the Goldbach conjecture, even Goldbach conjecture, in a similar range. So if you have an X in this range and you write it as the sum of 2 primes, they have some asymptotics of how many ways you can do that. One surprise is that in that case, actually, if X is actually divisible by this conductor, you can actually get the wrong number of representations as the number of sum of 2 primes. So there's a variant of the Hardy-Littlewood conjecture that predicts how often an even number X can be written as sum of 2 primes. It's just very similar kind of a singular series type thing. We know that hypothesis is false in the presence of a Siegel zero. Now, they were not the first to observe this phenomenon, but they gave a very strong version of it. Okay. And they also gave formulas. You can also count primes in short intervals and compute their variance and so forth, and you get some deviation from the pair correlation conjecture, which was also that conjecture was also previously known. Anyway, it's a nice paper. I recommend you read it. Okay, so these are the results I want to talk about. So for those of you who are not familiar with Siegel zeros, I haven't explained yet why the Siegel zero is so powerful, why it actually is so useful in number theory. So the basic reason is that it's a zero of the L function, and the L function has a certain Euler product. Okay, so if you take the reciprocal of the L function, as long as S is bigger than 1. So if you're to the right of this line here, this L function is an Euler product. It's a product of a bunch of numbers which are either bigger than 1 or less than 1. So if chi of p is plus 1, if this is a negative, if chi of p is minus 1, it's positive, and chi of p is usually either plus 1 or minus 1. It can occasionally be 0, but usually it's plus or minus 1. So if we have a 0 of really high quality close to 1, that means that L1 of chi should be very small, and we have estimates to quantify that. And so this reciprocal should be very large. So for S a little bit bigger than 1, let's say S be 1 plus say 1 over the log of the conductor, this product should be very, very large, which means that many of these factors should be bigger than 1 rather than less than 1. And so this sort of informally leads to the following heuristic that whenever you have a Siegel zero, it will encourage, it will bias the Dirichlet character to be -1 on most primes which are of about polynomial size in the conductor. So so you get good control when S is distance about 1 over log Q from 1, which corresponds to basically investigating primes which are close in log scale to the conductor. So if you're within range of the conductor, the Siegel's basically the Dirichlet character chi is picking out what numbers are prime. It's forcing the primes to live in quadrigonal residues. Another way of saying it is that chi of p is -1, and -1 by definition is also the Liouville function. So another way of describing this heuristic is that at the scales of the conductor, the Liouville function can be approximated in some sense by the Dirichlet character. And that's great because we understand Dirichlet characters much better. I mean, still not perfectly, but much better than the Liouville function. For example, the Dirichlet character is periodic. And so asymptotics are a lot easier, periodic function than a non-periodic function. And then there's a variant heuristic. So the Romain-Gold function is related to, it's the Dirichlet convolution of the Mobius function and the log function, which is kind of pretty close to also the convolution of the Liouville function with the log function. And if you believe that the Liouville function is like the character, then the Liouville function, the Romain-Gold function should behave kind of like the Dirichlet character convolved with the log. Now, this is quite a rough heuristic. In fact, literally a rough heuristic. It's only expected to be true for what are called rough numbers, numbers that are not divisible by small primes. Okay, because this kind of agreement is only expected for primes that are half polynomial size. If your prime is much smaller than the conductor, then it's not expected that lambda and chi have to agree. But there's this range where they agree. Okay, yeah. So there is this caveat which makes papers a lot longer. Okay, but morally speaking, we have these asymptotics. And so that's great. So I mean, so all these papers are kind of easy to explain if you kind of believe that these are really, you can substitute lambda for chi without any problems whatsoever. So, for example, if you are looking at a Chowla type correlation like this, and you want to understand this correlation, if you believe that lambda is really behaving like chi, you can just replace lambda by chi. And this correlation, which is hard to understand, becomes a correlation of Dirichlet characters. And this we understand. This is a vowel sum. And we have this big hammer. We have the base sum. Okay. And we have the Bay conjectures, which give you some cancellation. That's kind of morally why we can get Chowla type conjectures in Siegel 0. So, and in a similar spirit, if you have Siegel 0, then the Romain-Gold function, as I said, morally is like the convolution of chi and log. Now, the log function is not too far from the constant function 1. I mean, log varies so slowly that on any kind of reasonable short interval, it behaves like a constant. So log is about as difficult for analytic number theorists to deal with as the function 1. And chi is just a twisted version of 1. It's 1 on arithmetic progression. It's constant on arithmetic progressions. So as long as you're working at scales a bit bigger than the conductor, chi is also not much more difficult to deal with than the constant function 1, especially because of these Bay estimates and so forth. Chi convolved log you should think of as just sort of a slightly twisted and slightly more complicated version of 1 convolved 1, which is a very well-studied function. It's a divisor function, number of ways you can represent numbers as a product of two numbers. So, I mean, they're not exactly the same, but as a general rule of thumb, things that you can do for the divisor function, you have a good chance of also doing for chi convolved log, as long as you are at scales bigger than the conductor. So that you don't have to deal with character sums in short intervals, which is still a somewhat not completely understood topic. Okay, but anyway, if you buy into all those heuristics, then once you have a Siegel 0, a correlation, a Hardy-Littlewood type correlation, k-fold correlation on Romain-Gold, which is notoriously difficult, should somehow reduce in strength to instead a k-fold correlation of the divisor function, which is a better function. You can already see it in the Dirichlet series. The Dirichlet series of Romain-Gold is the log derivative of zeta, and so it has poles everywhere that this zero function, the zeta function is zeros. So if you want to understand Romain-Gold, you start caring a lot about where the zeros of the zeta function are, and as you know, we don't completely understand that question. But the Dirichlet series of the divisor function is a square of the zeta function. So it only has one pole, it has a pole at 1, and there's no other poles. So it is easy to understand, but still not perfectly understood. So if you just summon a 1-point correlation, then the Dirichlet series give you lots of information. But k-point correlations, unfortunately, are not easily attacked by a Dirichlet series. And in fact, even for the simpler sum, we only have good estimates for k equals 2. Okay, so pair correlations of the divisor function are understood. You can use Kloosterman sums or more advanced automatic form methods, and we have pretty good method of dealing with pair correlations of divisor function. But rather famously in number theory, we do not get to 3-point correlations of the divisor function. That is still quite difficult, basically open. Maybe in function theories we can do something, but definitely not in number theory. Okay, and this is the main reason why we can only handle at most two copies of that. Because current state of the output divisor function also kind of 2 copies of the divisor function. But the moment there's a breakthrough over here, there's likely to be probably to have a corresponding advance in improvement to our theory. Okay. Okay. So just a few more details. So I said there was this heuristic that if there is a Siegel 0, then within polynomial range of a Siegel 0, primes tend to cluster on the codec non-residue. So chi of p is usually -1, and there are very few primes for which chi of p is not -1. And the stronger the quality of Siegel 0, the more the same is true. So there's various ways to formalize this. Classically, you messed around with the Perron's formula, and you use something called the Dorian-Highborn phenomenon. We found actually that the best estimates to control Siegel 0 actually come from quite elementary methods. So the best estimates we can get actually are for exceptional primes. Okay, so a prime I call exceptional if it is not a quadratic non-residue. So that chi of p is not -1, it's either 0 or 1. So these should be quite rare, and the higher the quality of Siegel 0, they should be the rarer they should get, but only within range of the conductor. So one estimate that we have is that if you count exceptional primes in this sort of harmonic way between factor to the 1/2 and some x, you get some bound which has a log x, which you don't like actually, because this should only go like log x. But so there's a sort of log loss here, but you also gain 1 over the quality of a Siegel 0. So and for a strong 0, that's quite a good estimate. So you get quite good estimates. But this is saying that there's very few exceptional primes once you're bigger than, say, the square root of the conductor. You can maybe get this make 1/4 if you use biggest bounds, but we did try to do much better than that. And then if you're a bit less than square root, so like if you're within, say, between 1 over 2 nth root and 2 minus first root, you also get a bound, but the smaller you go, the weaker the bound gets. So like if you're between, say, q to the 1/4 and q to 1/2, you only get this 1 over eta becomes 1 over square root of eta. So the strength of the bound weakens. As you keep going down, it gets weaker and weaker, but you still get a reasonable range on which you have some estimates. I won't go through the proof. Basically, you open up Montgomery and Vaughan's textbook, and you look at what the asymptotics are for this particular convolution, 1 can involve chi, and there's lots of asymptotics for this, elementary bounds, upper and lower bounds for this, and you just plug it in, and you just use classical elementary methods, and you get these bounds. It's much better than where you get that complex scientific methods. But the upshot is that there's a certain large range of primes for which basically there are no exceptional primes, or very few exceptional primes. So the range is something like q to the 1 over log of the quality and q to the quality, up to some epsilons, which I don't want to talk about. Okay, so that is the precise statement that we, well, a more precise statement that we use. So, so as a consequence, once x is reasonably big, the practical upshot of this is that primes that are bigger than a certain threshold. So we pick a threshold for x to a small power. There's a certain x to a small power, which we call r, beyond which there are so few exceptional primes that the influence of these primes on all of these correlations is basically negligible, smaller than the main term. And so because of that, you can actually approximate things like the Liouville function by nicer things. Okay, so we don't quite approximate lambda by chi. That's not quite what you do. You instead approximate by a more complicated approximation for lambda Siegel. This is a multiplicative function which agrees with Liouville for small primes. So for primes up to this threshold, it is the Liouville function. But for primes above the threshold, we switch from the Liouville function to the Dirichlet character. So it's the Dirichlet character on rough numbers and the Liouville function on small numbers. So it's kind of this hybrid. And because there's so few exceptional primes beyond R, it's a good approximation. You can swap lambda by the Siegel approximant, and the errors are small. And then this Siegel approximant is kind of a sieved out version of the Dirichlet character. It's not as simple to handle as the Dirichlet character, but it is within range of existing methods. And basically, vowel sum estimates and some basic sieve theory, then that you handle any correlation working that to sieve. And then in a very similar spirit, there is a nice approximation to a Mangold function, which we call lambda Siegel, we basically take this crude approximate lambda convolved log. As I said, this is only a good approximation for rough numbers, but the lambda is supported on rough numbers mostly. So you just need to take this convolution and hit it with some sieve weight to restrict it more or less to rough numbers, and then that's actually a pretty good approximate. Now, as it turned out, we actually chose a path that made it more difficult than we needed to, because there's a number of choices for what sieve to put here. And we chose the Solberg sieve, which turned out to not be the optimal choice. And that made up a little bit longer. There's a later observation that so Mathematic and Markowski observed that actually you could take instead what's called the beta sieve, or the Rossov-Vanich sieve is also called, and that gives actually better estimates. But anyway, that's a technical detail. It makes all the papers longer. But as I said, roughly speaking, it means that you can approximate lambda by something which has the strength of the, it's a twisted, more complicated version of the divisor function. And the techniques that are used to understand the divisor function can be used to handle this. So we use basically the most basic estimates for the divisor function to conclude themselves, and a lot of unpleasant calculation. Okay. All right, so these are our results. Now, there is the objection that's often raised in this particular corner of the subject that these results kind of are vacuous in the sense that they rely on hypotheses which no one believes to exist. So yeah, so these are sometimes called illusory results or ghostly results. I think, yeah, sieves involving the sequence are something called the illusory sieve. Well, I still think it's good to explore this case. Okay, so for example, one thing that may have happened, I think this is very remote, but if we keep investigating consequences of the Siegel zero, we might actually find two consequences that contradict each other. That'd be great. That means there's no Siegel zeros. That's not my idea. Many people have tried to make that happen. But the other thing is that yeah, it also kind of gives you it's expected to somewhat be the worst case. So it sort of gives you sort of the limit of what you can expect to do without having to solve the Siegel zero problem. But ideas like this can be used to sometimes get unconditional results that are true regardless of whether there's a Siegel zero or not. So if you can prove something when there's a Siegel zero, and if you can prove the same theorem when there's not a Siegel zero, then you can prove the result in all cases, often ineffectively. But yeah, so I'll just mention briefly one thing that we're able to do, not exactly using these techniques, but sort of similar methods, is that we were able to show, for example, the Mobius function is expected to be very uniformly distributed on large intervals, say from 1 to n, and there's a precise way to characterize this called using what are called the Gauss uniformity norms, which I will not talk about here, but there's a certain norm for which the trivial bound is 1, and it was known through work of Tammy and Ben and myself that you can get some cancellation, that these bounds actually go to 0, these norms go to 0 as n goes to infinity, but our bounds were quite ineffective for multiple reasons, which is a whole talk in itself. But we were able to get some effective bounds, some effective decay, not super strong, but of log type for these functions, and actually, in fact, even effective, which was a bit of a surprise to us. Which has other applications, like we can't use it to count primes, but you can count solutions to other linear equations primes, and you can now get effective error estimates on that, which also have this sort of log n type error. Okay, now
Terry, I'm a bit confused here. As you pointed out, if you make an argument which assumes that there's Siegel zeros and get somewhere, and assume that they're not, and you get somewhere, then your result is usually almost certainly ineffective. So when you say you're doing something similar, you're getting unconditional results, and then at the bottom you say they're effective. Yes. Are they really effective, or you're not going through this?
I mean, because we have a little bit of effective control on the Siegel zero. I mean, we don't use Siegel zero, but because we only seek log type bounds, and so the even just the class number bound on L functions, I think, similar. I think for what we do, we don't even need the Goldfeld type stuff. Yeah, if you want to log into a power, like you maybe log into a small power, you might have a chance to be effective. I have to think about that. If you want to log into a large power, definitely you'd be ineffective. Okay, but yeah, it's kind of cheat. Yeah, it's because our bounds are kind of weak that we get around that problem. Yeah, so I won't go into exactly why. But yeah, as I said, the rough idea is that yeah, you split in the case where there is a Siegel zero or there isn't. If there isn't a Siegel zero, then it turns out that the distribution of the Mobius function in affect progressions is quite well understood. There's a nice error term which is exponential of log to a small power, and the key point is that it's like double exponential of log n. So you get quite good bounds on the Mobius function in affect progressions, and then with inserting that into existing techniques, you can also get good bounds on the correlation of Mobius functions with these things called nil sequences, which I'll talk about here, which are also quite good double exponential of log n. And then you have to hit it with something called the inverse theorem for the Gauss norms, which until recently was ineffective. But thanks to the work of Freddie Manners here, there are effective bounds which cost a log in the bounds. You insert this sort of rather good bound and you pass it to the inverse theorem, and out on the other side comes a log type bound. And that's roughly speaking the story when there's no Siegel zero. Now, when there is a Siegel zero, what happens is that you can construct an approximant, which we call mu Siegel to mu, which it's not quite as simple as the approximant that I discussed for lambda previously, but it's in a similar spirit. You have to have quite a good approximant. The key property we need is that the difference is really, really well behaved in that on arithmetic progressions, the asymptotics of this difference are as good as what you have in the no Siegel zero case, for which you also get this quasi-polynomial gain in the error estimates, and that takes a bit of work. You actually have to choose this approximation quite carefully, but you can do it, and you actually still get effective bounds on that. And so the same argument actually gives you good uniformity bounds on this difference. And then the Siegel approximation is actually simple enough that you can control the uniformity norm of the Siegel approximation by hand. And you can also get bounds of log type. In fact, I think even log type for the Siegel approximate, and even still effective. I think it's the Gauss norm of mu Siegel is effectively bounded by a small power of log n, one of a small power of log n, and then you just apply the triangle inequality, and then you can get the bounds from you. And you can do a similar thing for Mango and so forth. So this is a sort of a so even though the results I talk about mostly are sort of about they're illusory in some sense, some of the techniques can be used to prove some unconditional results. There is work in progress, but we don't have I think we're not quite comfortable to announce results yet. So we talked about the Siegel zero consequences for the Chowla and Hardy-Littlewood conjectures. The next step is to deal with polynomials. Okay, so there are conjectures. So there's also a Chowla conjecture for the correlation of lambda evaluated at say n squared plus 1. That's believed to be literal of x. And there's something called the Bateman-Horn conjecture, which gives you a conjecture asymptotic for the similar thing for the Omega function. This we would love to apply the same techniques to. Okay, so again, morally, you can replace lambda by chi here, and you can replace big lambda here by chi control log, and those type of sums we know how to do, how to handle. Again, very some estimates would handle that the chi thing here, and I think some sort of Klussmann some estimates still work over here too. But we've encountered a technical difficulty that we are still struggling with. So I told you that when you have a Siegel zero, it repels, it makes most primes unexceptional. It forces most primes to live where chi in this range, in the polynomial range. Most primes are codiagonal residues. So there's some exceptional set. And in the Chowla and Hardy-Littlewood cases, we can show that the contribution of those exceptional primes is negligible by some basic set theory. But now we are summing over a sparse set. The n squared plus 1s are quite a sparse subset of the integers. And their prime factors also are somewhat sparse in this range. And there's this annoying scenario that maybe all of the prime factors of all the n squared plus 1s that we care about just happen to hit this very small exceptional set of exceptional primes. And that has been very annoying. And so we are not able to get results as strong as what we would like, but it looks like we can still get some non-trivial bounds. For example, for the Liouville, I think we can prove that the bound here is bounded by 1 minus a small constant times x. So the trivial bound for this is x, but we can get a tiny gap, but we can't get little of x, which is what we really like. So this is still work in progress, but I just want to, I think we're comfortable at least announcing that we are working. Okay, I think that's all I have. So thank you very much.
Questions?
Is n squared the critical sparsity?
Right. Yeah, so that's the funny thing. So the maximal quality of a zero equals zero can get in principle as big as conductor 1/2, effectively. So that's the class number, and you can save a log or something if you use some high powered stuff. But yeah, so there was one scenario if you take a Siegel zero, which is ridiculously high quality. Yeah, so basically class number is almost 1. Or that's not quite. I always forget positive, negative discriminant. Anyway, but if it's that super strong, then actually, yeah, the n squared plus 1 is the critical sparsity, and you might possibly be able to do something in that one case. But that case is like really expected to not occur because I mean Siegel's theorem says that doesn't happen ineffectively. So there's at most one zero for which that statement could possibly be valid. Yeah, but yeah, that's yeah, it is somehow the critical density. Yeah, of course.
We can't treat the divisor function for polynomials of degree larger than 2.
That's correct. Yes. Yeah. So yeah, that's the other reason. Yeah. Yeah. No, this problem is already at the limit of difficulty with many. Yeah. This would be this will probably the last thing we can prove in this direction. Pretty much. I mean, maybe other quadratic forms.
I have a question. So this Tao and Schusterman trick is also based on this some periodicity. So you can kind of expect the non-Siegel, not having a Siegel zero to, or sorry, having a Siegel zero to work to kind of be able to transfer various results that are true for function fields.
Quite possible. Yeah, there is an analogy. Yeah. So certainly the Tao-Schusterman result is based on not this heuristic. So the main heuristic here was that Siegel zeros imply that the Liouville function can be approximated by a Dirichlet character in a certain sense. It is true that the key starting point of Tao and Schusterman is that for certain function fields, you can also approximate the Liouville function by Dirichlet characters in a different sense. I think on shorter arithmetic progressions, you're able to get even an exact algebraic identity. And so they do reduce. So the type of correlation we study here, they similarly reduce to a different type of correlation involving Dirichlet characters, which they are still able to control, I think using more advanced Bayesian estimates than what we do. Yeah, so it's, and they have parallel problems. So again, they can only handle pair correlations of Omango. They can't handle high order correlations. I think it's a similar obstruction. Maybe not exactly the same, definitely. But yes, one could imagine that if there's further progress on the function field side, maybe there's a possible pair analog in this Siegel zero world. Yes.
With Chowla's conjecture, things become a little bit easier if you consider logarithmic averages. So I was wondering, in the presence of a Siegel zero and logarithmic averages, can you say more? Or
we have not found a way to synergize these methods. I mean, part of the problem is that on the logs, well, yeah, and actually maybe okay, not currently. Okay, so the main advantage of the logarithmic averaging is that there's this additional method available, like this entropy decorat method, which is another way to control these averages, but it gives rather weak bounds, and it doesn't play well with other methods. It's sort of a very general technique that doesn't use the number theoretic structure of the functions you're averaging. So I can't see a way to combine them, but so yeah, we don't get any better results by log averaging. But it's possibly if there's another way to use log averaging than the entropy decorat method, then maybe there's something to do. This thing can't hurt.
If I may, Terry, yeah, great talk. If I may say something about a name and a principle, and that is, as you know, Henrik and I added the word Landau to Landau-Siegel.
Oh, yes, yes.
And there's a reason, because there's something very conceptually deep there. And that is, it's not about an infinite sequence. That's why I wanted zeros in your title, but your word type is, I understand. But the point about the Landau-Siegel zero is one bad guy, as you pointed out, one bad guy controls, it's not, you don't need an infinite sequence. You don't need, so just one guy. So that's, there's one exception. So it's not an infinite sequence. It's one guy which controls the q to the epsilon. And it's quite remarkable that and that was the insight that Landau had, which Siegel then, I can tell you the history. I heard it from Jürgen Moser, who was Siegel's assistant in Göttingen many years ago.
Okay.
And I'll tell you the exact story of the history. So in fact, both papers appear in Acta Arithmetica 1 before the war, and barely available. And the one paper of Landau, and there's a paper of Siegel. And funnily, Siegel's paper doesn't refer to Landau's at all, where he did get the idea from Landau.
Okay, it's true. Actually, maybe we should call them Landau-Siegel zeros.
No. I think there's a concept there where it's actually it's one guy controlling the whole story. While in your story, in order to get twin primes, say where Heath Brown starts, you really need an infinite sequence.
Okay.
I mean, you've quantified everything to the point where you're saying in which ranges what controls what. But if you want to make the statement that twin prime follows from Landau-Siegel zero, you can't. You have to say Landau-Siegel zeros, and you have to have the notion of a sequence.
Yes.
It's just a matter of terminology. And
okay.
anyway,
Right.
it's just names. Lovely.
Okay.
There are no further questions. Let's thank Terry again.